Today we're going to talk about this incredibly powerful, totally invisible force in machine learning. And I want to be clear, this has nothing to do with what a model thinks or prefers. No, this is about a fundamental force that literally dictates its every single move.
So, in our last explainer, remember how we talked about data creating a kind of map? You know, this huge complex space where similar ideas naturally group together? Right. But a map is just static. It just sits there. So today we're going to look at the dynamics. What are the forces at play inside that map? I mean, what actually carves the paths and makes a model move from point A to point B while it's learning?
And the answer, well, it might not be what you think. It has nothing to do with meaning or understanding or what a model likes. It's about one thing, pure mathematical force.
All right, so here's how we're going to break it down. First, we'll shift from thinking about maps to thinking about forces. Then we'll see this invisible pull in action. After that, we're going to make that force visible. And we'll wrap up by talking about why this is all really about physics, not psychology. Okay, first up, let's make that shift from the static picture of data to the actual engine that's driving everything.
Okay, so the engine behind pretty much all of modern machine learning is something called gradient descent. Now, the easiest way to get your head around this is to picture a ball on a really hilly landscape. The whole point of training a model is to find the lowest spot in that landscape, the bottom of the deepest valley, because that's the point where the model makes the fewest errors. So gradient descent is just the rule that says always roll downhill in the steepest possible direction. It's the fastest way to get to the bottom.
And that direction, that path of the steepest, fastest way down, that has a name. It's called the gradient. You could think of it like a compass that the model is forced to follow. It doesn't ask questions, it just goes where the gradient points. Okay, so that's the theory. But what does this pull actually look like in the real world? Let's take this invisible force and see it in action. So what we have here is a pretty standard sentiment classifier. Its job is super simple. Just label a piece of text as positive or negative. And it learned how to do this by looking at millions and millions of sentences scraped from the internet. Now here's a really critical detail, and you're going to see why this matters in a second. Those millions of examples it was trained on, they are not evenly distributed, not even close. Some phrases and ways of speaking show up way more often than others.
All right, let's feed it our first sentence. I will do the needful. Now, this is a perfectly normal, polite phrase in, for example, South Asian English, but look at what the model says. It calls it neutral, maybe even a little negative, and its confidence is pretty low. Okay, now let's try a phrase that means basically the exact same thing, but is more common in American English. I will take care of it. The meaning is identical, but just watch the output. Bam! The model flags this as highly positive, and the confidence just shoots way up.
So what on earth is going on here? To a person, these two sentences mean the same thing, but the model's reaction couldn't be more different. Why? Why did the label and the confidence just swing so wildly?
Let's find out. It's time to make that invisible force visible. And we're going to do it by connecting the model's behavior directly to the density of the data it was trained on.
And here it is. This is the answer. When you actually look at the training data, the phrase "take care of it" shows up millions of times. It's this huge, towering bar on the chart. And "do the needful"? It's barely there. It's a statistical ghost, just a tiny sliver. So how does this connect back to gradient descent? Well, think of it like this. During training, every single one of those millions of examples gives the model's internal knobs a tiny little pull. It's like a tiny nudge that says, hey, when you see something like me, turn your knobs just a little bit this way so you get better at predicting my label. And here's how those tiny pulls become an unstoppable force. You've got each data point creating a little pull. Then all those pulls from millions of examples, they all combine. And so the patterns that show up all the time, they create a massive collective gravitational pull. They're the ones that carve out the deepest valleys and the steepest slopes. They create the strongest gradient. And this brings us to an absolutely unbreakable mechanical rule of machine learning. This isn't a suggestion, it's not a guideline, it is the fundamental law of its physics. Optimization always moves in the direction of the strongest gradient. The model has zero choice, it just follows the slope. So here's the takeaway. Those sparse areas of the data map, where "do the needful" lives, they just can't compete. The pull from the dense regions is just too strong. The majority always wins. And it's not because its data is better or more correct. It wins because it creates the most powerful force, the steepest gradient, and the entire system is built to do one thing: follow that gradient.
All right, let's pull all of this together into a new way of thinking about this, because we have to stop thinking about psychology and start thinking about physics.
You know, a common question I get is, well, can't you just tell the model to be culturally neutral? And sure, you can try. You can put some rules on top of it. But that's just a patch. It's a surface-level fix. Those rules are working on the final output. But the real problem is deeper. The gradients, those forces from the data, they've already shaped the core behavior of the model. It's like yelling at a river to flow uphill after the canyon has already been carved for 1,000,000 years. The path is already set.
So let's just recap the whole thing. The training data creates a landscape of gradients. Those gradients apply real mathematical force. The dense parts of the data pull way harder than the sparse parts. And the model's training just follows the path of least resistance. It's that simple.
And that leads us to the single most important idea in this entire explainer. What we often call bias is really just the path of least resistance in mathematics. The model didn't choose this path. The data carved it.
So if the problem is data density, you might be thinking, can't we just add more data for the rare cases? Well, it's not quite that simple. In fact, sometimes adding more data can actually make things worse. Join us next time when we're going to dive into why that is and explore the constant battle between signal and noise that is at the very heart of AI.